So section 2.1 is just a slew of definitions about what matrices are, what their parts are, and what various terms are that can be used to describe them. So the very first, most basic one is just that a matrix is a rectangular array of numbers. And so this means that, let's see, say we take the matrix A to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are just a bunch of numbers written in a grid, and then we put some brackets around it like that. And so then we also talk about the entries of a matrix. So for instance, this guy right here, well, first off, if we have a matrix A, then I might talk about the entries in it. So the ijth entry of A will usually denote by a lowercase ij like this. And when I write this, I mean that the first index here tells you which row you're looking at, and the second index, so the j, tells you which column you're looking at. So if we go back to the matrix that I drew here, this entry here, this is going to be in the 1, 2, 3, third row and second column. So this would be A sub 3, 2, as opposed to, for example, this one over here, which would be A sub 2, 3. Okay, so those are matrices and their entries. So two matrices are equal if and only if equal if and only if they have the same size and the same entries. And so if you haven't seen this IFF, the if with two F's right here, this means if and only if. And it's something I often say when I'm giving a definition. It means that it's equivalent. So for example, something like the matrix 2, 3, minus 1 and 2, 3, minus 1. These are not the same. These are not equal matrices because one of them, well, they have different sizes. One of them is a 1 by 3 matrix. The other one is a 3 by 1 matrix. And so we have a special name actually for this. So a matrix with only one row or column is called a vector. And so here we have examples of a row vector of length 3 and a column vector of length 3. Okay. The next idea that we have is the transpose of a matrix. So the transpose of a matrix is formed by interchanging columns and rows. And so if I have some matrix, so let's go back to this one that we had before here. Let me just copy and paste it and tidy it up. Bink, bink, bink. Ba-dum, ba-dum. Okay, so if that's A, then A transpose would be written first off, A with a superscript T like this. And then I would just take each of the rows and write it as a column, or take each of the column and write it as a row. Either way, you get the same thing. So 159, the column becomes 159, the row. And 2610, the column becomes 2610, the row. And so forth. Oh, I already used that color. Here, let's go orange. Okay, so there's the transpose of the matrix. So over here, back up in the last definition, if this first row vector we call, let's say call it R for row vector, it's not equal to this column vector C, but we do have that R is C transpose. Okay, moving along, a matrix is square if it has the same number of rows as columns. So, for instance, this guy is a square matrix. This guy is a square matrix, etc., etc. So here we have a 2 by 2 matrix, and here we have a 3 by 3 matrix. And so I forgot to mention, but I'll talk about matrices in terms of their size, so and shape. So for instance, over here we had that A was a 3 by 4 matrix, so I would write that as M3 4. And then we saw that A transpose was a 4 by 3 matrix. So I'd say it is an element of M for 3. And so this little symbol here, this funny E, this means element. So script M is the collection of all matrices. So this is the set of all matrices with 3 rows and 4 columns. And so this little expression is just saying A is 1. A is a matrix with 3 rows and 4 columns. Maybe I'll write that down. A is a matrix with 3 rows. Whoops. And 4 columns. Okay. So then for the next definition here, where we're talking about square matrices, I might say that actually let's give the second one a different name so they don't conflict. So I would say that A is an element of 2, 2, and B is an element of 3, 3. So A is a 2 by 2 matrix and B is a 3 by 3 matrix. Except in the case of square matrices, typically we actually just are lazy, and instead of writing this one, we would instead just write M2 or M3, and then it's understood that it's square. Okay. The diagonal of a matrix is the entries with equal row and column indices. So that means it's for the matrix A, the actually here, let me erase that. The diagonal of A is A11, A22, A33, etc. Depending on how big A is, maybe it's an n by n matrix. So in other words, we're looking at all of the II entries. Those are the ones on the diagonal. And so going up to the previous example here, the diagonal of A is this part right here, the 0 and 3, and the diagonal of B is this part right here, the 3, 4, 9. You only have a diagonal for a square matrix. And you might be thinking, hey, there's another diagonal. What about the diagonal that goes from bottom left to top right? Well, we don't care about that one. We don't use it for anything. It never comes up, so forget about it. It's worthless. And then the last idea that we have for this clip is the idea of the trace of a matrix. So the trace of a matrix is the sum of its diagonal entries. So the trace of A, for example, from the previous example would be 0 plus 3. So that would be 3. And the trace of B would be 3 plus 4 plus 9. So that would be, oh gosh, whatever, 16.